Hello, everybody. Welcome to lesson number 2 in our science course. Today, I've got some questions that we're going to talk about, and we're going to address them all using this theory called kinetic molecular theory. And then after that, you'll have some work to do. But here are our questions for today. They are: what is temperature? What is the relationship between temperature, energy, intermolecular forces, and the states of matter? And then what are heating and cooling curves, and what do they tell us? So in our lesson today, we will address all these questions. You will learn what kinetic molecular theory is and how it applies to all of these things. All right, so let's get into it. Our first question today is, what is temperature? So, I would like you to think about that. Perhaps you can pause the video at this point and chat with one of your neighbors and then write down what you come up with. So, let's take 1 minute to do that. Try and answer what is temperature. Just give me your best shot at defining what temperature is. Okay, so hopefully you and your buddy came up with a definition. Before I tell you what my definition is, or why it's important for today, I want you to think about another question. So, here's the second question. What property or value is temperature directly related to in connection with the particles of a system? And you may find a hint on this slideshow. So again, take another minute. Perhaps this one, just write down your answer. What property or value is temperature directly related to in connection with the particles of a system? As we've been talking about how particles interact when thinking about different states of matter. Take a second to think about that. Okay, so thinking about this question may have helped you redefine temperature, but temperature, if you look at this little graphic here, we can imagine that all of these tiny little things are particles, right? Maybe this is a liquid or a gas, and they're all moving around past each other, right? And the property we can see here at play is their motion, right? Or their velocities. They have different velocities, different speeds. And so each of these particles has motion energy, which is kinetic energy, right? The energy of motion. All things in motion have kinetic energy. And so temperature is directly proportional to the average kinetic energy of a system of particles. That basically means that temperature is a measurement of the motion of all the particles in the thing you're looking at, right? So if that's the air, if that's a gas, we are measuring the average amount of motion energy of all of the particles in the gas. So that's actually how thermometers work, right? You put them in a room. If it is a hot room, they start to rise up to the temperature of the room. That's because the gas particles that are moving are colliding with the liquid in here and giving it energy, which pushes it upward, right? So it's a measurement of the average motion energy of all those collisions with the liquid particles. This is core to what kinetic particle theory is, and you can kind of see that in the name, right? Kinetic. Kinetic is a sciencey way of saying motion, right? So the motion particle tiny bits theory. And this theory will help us explain these transitions, these changes of state, right? So the kinetic particle theory basically states that matter is composed of tiny particles that are constantly in motion, right? We know this. We talked about this a little bit yesterday. Even the solids are moving. Yes, even your chair, all the things. Every particle has some amount of kinetic energy. And we now know that as the temperature increases, the particles are gaining more kinetic energy. Uh, so we had a diagram like this last lesson, and it might have said temperature pair, I don't remember. But you can think of this as temperature or as increasing heat energy, or decreasing temperature, decreasing heat energy, right? Because they are proportional to each other. Temperature is a measurement of kinetic energy. And then the last part of this is we know that particles are attracted to each other through intermolecular forces, right? These forces happen because of the electrostatic or electromagnetic force, which is a fundamental force, right? The positives and the negatives that exist within these particles attract them to each other. Um, so we know kinetic motion when we get to like a solid, right, it has less motion than a gas, has less heat energy, but it has stored energy in its lattice. So these intermolecular forces create these bonds that store energy, right? There's potential energy in there. So as we begin to think about these changes of state in a new way, I want you to think about them in terms of this kinetic particle theory. Heat, energy. Energy is the key thing here. And if you don't know yet, if you haven't seen this in physics yet, um, there is a law called the conservation of energy, which means energy cannot be created or destroyed. So it's energy is being exchanged in these interactions, but it's never disappearing. It's never going away, right? It's just being changed in some way or another. So let's kind of talk through each of our phase transitions through the lens of this kinetic particle theory, this motion particle theory. Um, for instance, melting. When a solid is heated, right? So we're giving the solid heat. Maybe you're putting an ice cube on top of a fire, right? You are giving it more kinetic energy, right? The heat gives it motion energy. So each of these particles start to vibrate faster. When you reach the melting point, the particles have enough energy to overcome the intermolecular forces holding them in place, to overcome those lattice bonds, right? So if you, um, let's say it's you shaking a solid, if you shake certain solids fast enough, they will break apart, right? You can imagine that happening at a very tiny level, like a molecular level. That's what's happening at the melting point. The heat energy, which is coming from something like a fire, is giving all of these particles energy, right? Eventually, they get enough energy to break free from their fixed positions and they start to move more freely. And that's what we call a liquid, right? Um, so, when we think about it in reverse, right? Freezing. When a liquid is cooled, particles lose kinetic energy and slow down, right? So, that energy is being taken away somehow. Perhaps you put your liquid in a cold place, that energy goes into the atmosphere. Um, at the freezing point, particles transition to an ordered solid state held together by those intermolecular forces, right? Um, so when they freeze, they store energy in those bonds and they have less motion. Boiling. So now we're moving from a liquid to a gas, right? When a liquid is heated, the particles gain more kinetic energy. This causes them to move faster and collide with greater force, right? At the boiling point, the particles break free, so they completely break free of those intermolecular forces holding them. in a liquid state, and then they can spread out and move in all directions, right? So if you give a liquid enough energy, it will break free from those bonds, those forces, and become a gas, right? You can imagine all of these things have a small amount of attraction between them, so they don't just move freely in a space. But if you give them enough energy, they can break free from those and become a gas. And then, oh, evaporation. Yeah. Evaporation is similar. It's the same idea, right? It still has to do with energy and motion energy. But evaporation can happen at multiple temperatures, right? So it occurs at a range of temperatures at or below the boiling point. The particles in a liquid have varying kinetic energy. So if we think back to that very first graphic with all of those particles moving around, some of them are really fast and some of them are kind of slow, right? The temperature is the average, but each particle has a different amount of energy. So some particles at the surface of a liquid can gain enough energy to overcome the forces, the intermolecular forces holding them, and they can escape. So at the very top, like this is a pond, right? Of the pond, some of those particles will get enough energy. Maybe the sun is shining on them, heating them up, and they will escape, and you can get this nice mist, right? Or we had this picture last week too. Your towel will dry in the sun because of evaporation. Slowly, each of the liquid particles gets enough energy to escape. Um, the rate of evaporation increases with temperature. That kind of makes sense, right? More temperature means more kinetic energy that is available to these particles, which makes them more likely to escape. Condensation, so going in the other direction, from a gas to a liquid. When a gas is cooled, particles lose the kinetic energy and slow down, right? Eventually, they've lost so much energy that they collide with another particle, gas particle or liquid particle, and they don't have enough energy to escape, so they get stuck, right? Particles come closer together and intermolecular forces form. Um, as this happens, more and more get stuck, right? Because they don't have enough energy to escape. So you might see something like this happening on your windows in the morning or on the grass in the morning time, because at night it gets colder and the water in the air loses energy and it collects on the grass, right? Or even clouds are an example of this. You can get water particles collecting high up in the sky together.